technology.
I was the kid who fixed the VCR in everybody's house. Yes, VCR.
So we're good?
Yeah, go for it.
Great. So Tristan just mentioned that he is his most recent graduate student. And so I was thinking about what am I most recent for, like in connection with Pete. So that's one thing that I saw. So I'm probably the most recent student of Pete who he introduced to Lisp programming language. So I've been telling people that like when Pete introduced me to Lisp programming, so there's one benefit that he mentioned. Like if you are really an expert at Lisp programming, you can claim that you're in the top 10 in MIT. Well, for any other language that you will really struggle to get to the top. So a lot of the things wouldn't have been possible without Pete. And so in today's talk, I'm going to be talking about my current research mostly, but as the talk goes along, I will point out the connections to Pete and then how he has cultivated the skill set and the research knowledge in me regarding those application areas. So I think people probably have took time to read the names and the affiliations. So I will just skip that. So is this?
Try the other one.
You just have to click inside the slide.
Try the space bar.
I guess you really teach your students good PowerPoint skills.
So I think the mouse works. The keyboard doesn't work, the mouse works. So right now I'm in Northwestern University. And then the Northwestern University has the teaching affiliated hospital chain, which includes 11 hospitals. And then the patients that's in the enterprise data warehouse is about 8 million so far. So this is probably outdated infographics, but so far the numbers of the patients have reached 8 million patients. And fortunately, we have access to all of those in the enterprise data warehouse. And so this would be actually a really powerful resource to use and then also partially drives the research that I'm currently doing. And so the data warehouse actually supports from data engineering, research analytics, application development, and data warehouse operations. But those are more like operational. And then for research, that's us. But beyond the EDW in Northwestern Medicine, we have actually also have a nationwide research network, which is called eMERGE. Stands for Electronic Medical Records and Genomics. And so within this eMERGE network, I think Harvard is also part of it. And then we have institutions from the Midwest and also the West Coast. And so all of us partner up together so that we can share our patient data and then genetic data in order to drive the findings between the genetics and their association with the phenotypes of the disease. So within that network, I'm actually the co-chair of the phenotype NLP working group. So we try to use NLP techniques to drive the phenotype algorithms in order to find and define the patient cohorts to facilitate the downstream applications and research on the disease genetics association. And then within Northwestern University, I'm also the chief AI scientist for the Clinical and Translational Science Institute. So basically this brings together all the affiliated hospitals with Northwestern Memorial Healthcare chain and also Chicago-wide CTFC consortium. We try to bring everyone and everyone's data together, and then we try to facilitate research that discovers the novel phenotypes and the novel associations between the genetics and phenotypes. So with all those data that we have access to, so this really boils down to the research that we are currently doing. And as I said, that would be impossible but for people. So originally I started out in clinical narrative text, natural language processing. And then after a few years, I told Pete that I want to do something else too. I want to work in structured EHR data, let's say limit data or other time series data. And Pete said yes. So he let me do it. And then so that's what got me into medical time series. And then a couple years later, I asked Pete again, well, I want to also do something else in genetics. And then again, Pete said yes. And then that's how I got into the omics research, and especially looking for genetic data and their associations, genetic variants associated with multiple diseases, including ASD and hypertension. So just to think about like how many advisors would let students do what they want like multiple times and expand their research areas. So this is truly a remarkable thing about Pete in supporting his students and his trainees into expanding their research interests. And of course, I want to point out that Pete does not say yes to everything. So I remember the first time I came out to Pete and I was telling him, well, Pete, I wanted to have a chapter in my thesis that does research on convex nonlinear optimization. And then he said, well, you need to be sensible. Let's start it now. So I think Pete has the great taste in selecting his mentees and also a great taste in choosing or navigating or guiding what's the best for the mentees. So with Pete's influence, so I started out in natural language processing, and now what I'm doing at Northwestern, one of the big initiatives that we're trying to push out is this bulk NLP to really power research and development and business intelligence. So the idea is that look at medical schools, like few of those thousands of faculties in medical schools have NLP capabilities, but we do have. We're probably like one of the rare species. So I was thinking that why not just scale up our capabilities and then make the NLP pipelines run on all those nodes in Northwestern's enterprise data warehouse. And we can run customized and standard NLP pipelines and then deposit the structured information extracted from the nodes and then put them in the common data model table so that when researchers want to use the structured information from the nodes, they do not need to run NLP again, but they just need to write up SQL queries and then query them off the tables. So this is one of the big initiatives we're trying to push out. And so far we have touched oncology and also cardiovascular medicine. And then we're trying to expand this to all these clinical nodes for the 8 million patients in Northwestern medicine. And then we are also doing, like besides this engineering work, we're also doing research, like trying to improve on the state of the art. And then one of the research that we were doing is to try to use the sequential of new novel deep learning methods, including recurrent neural nets to convolutional neural nets, and also graph convolutional neural nets to really drive the performance for relation extraction in clinical nodes. So why relation extraction is important? It will facilitate a lot of things, for example, adverse drug event detection. So if you can recognize the relations between the adverse event and then the medications that are stated in the clinical notes, you can actually build a EHR-based ADE monitoring system. So that's why we're working on this problem. And then the methods that, the automated methods that we set up in is actually a second level graph convolutional and recurrent neural net model. So if you look at the image, so this is actually a graph built on dependent depositing results. So it integrates the syntactic information and also the semantic information of the medical concepts stated in the sentence. And then we were feeding them into a graph convolutional nets on top and put on top a recurrent neural net bidirectional LSTM. And then we were trying to use this architecture to drive the extraction of the relations between, for example, treatment and the medical problem. And so this is the architecture. We have the bidirectional LSTM layer and then the graph convolutional layer. And then everything is fed in regard to the segment, those sentences segment that comes regarding to the two medical concepts. And then so we have actually achieved much better performance compared to all previous state-of-the-art competitors from the, this was taken from one of the ITV2 challenges, and also thanks to that. And so we actually have outperformed greatly when compared to all those state-of-the-art systems in the challenge competition. And then another thing that we are setting out to do is to use deep learning for long text understanding in NLP. So in this example, I'm going to show you the methods for trying to understand obesity and its 15 comorbidities. So this method was really combining the lexical information with the knowledge graph information, especially from the Yuan labs, and then we're combining the word level embeddings and then the concept level embeddings to really drive the phenotypes of the obesity and its comorbidities. And so, but we are not only just looking at deep learning methods, we are also looking at factorization methods. For example, in tensor factorization, we try to tackle the problem of cancer phenotype regarding, for example, lymphoma subtyping classification. So the idea, the motivation is try to automate the task of lymphoma subtyping because so far it's a very expert-intensive approach and subject to selection bias and also inconsistencies and no cases to class ratio. What we wanted to do is, so we want to drive explainable machine learning in that what we're going to present to physicians is similar to what they see in the WHO classification criteria. So in the criteria, what they see is a panel of the test result, immunophenotypic test result that characterize the patient's subphenotypes. And so what we are doing is, first we extract those relations between multiple medical concepts like CD cell antigens and also the link cells and also the expression levels. And those relations characterizes the immunophenotypic test result. And by using tensor factorization to group those relations, we can actually link those relation groups, which is equivalent to panels of the test result to patient subtypes. And then we have similarly been doing translating this idea to structured medical data in that we use the trans groups of patients' physiological fluctuations and then link them to multi-organ dysfunction problems and then link them in turn to outcomes such as mortality and also readmission. And then we also have been looking to expand the idea to other disease subtypes, for example, in Alzheimer's disease. In particular, we're trying to identify from EHR data whether we can identify risk factors that predispose the patients from progression to mild cognitive impairment to Alzheimer's disease. And then besides the NLP and structured data, we have always wanted to try to combine whatever the patient's data that are available in order to create a comprehensive view of the patient's pathophysiologic profile. This goes back to what Zach and Ken were debating on. Who cares about whether we have complete patient data? So I was actually among the camp that who cares. So by combining the phenotypic data with the whole exome sequencing data for hypertension patients, we're actually being able to subtype those hypertension patients. Because if you look at those patients, only 50% of them respond to antihypertension drugs. So clinicians think there are subtypes with more homogeneous characteristic that will respond to targeted therapy in a more uniform way. So that is where we're after. And then from those solid bases, so this is actually happening after I graduated from Magi. And then so I continued on the tradition to expand my horizon. And then we also started looking into medical imaging data. And so we're trying to look at imaging data between chest X-rays and also CXR data from Mimic. And first we built a Bayesian generative deep learning model that really put a confidence score on the medical imaging classification. And then we were thinking that by using graph convolutional network, we can actually build a graph that connects the multiple image that either belongs to the same patient or belongs to the same group, age group, or belongs to the same view, because those images, they bear similarities, they bear relations. While if you are classifying images independently, you ignore those relations. But if you connect them with the graph model, we can actually take into considerations of all those connections and make your predictions more interpretable, because if you just think of you have completely converse classifications on the images belonging to the same patient, that's inexplainable, right? But for our method, we try to take in such connections into consideration so that we're not only more consistent, but also more explainable. So with that, I will conclude my talk, and then I will emphasize again that all this would have been impossible without Pete's mentor and guidance. So he has been a tremendous mentor to me, to others, and also his influence has impacted not only us, but also our students. Thank you.
Sorry. Are they on the drill on the?
Hey, right there. You check your email. Or send you the coordinated slides to draw on. Thank you, sorry. No, that should be good. Yeah.
Do you have your forward these to me and I'll add it. Do you want to add it? Yeah. Okay, perfect.
Sure. So I'm Chris Casa. I'm an assistant professor of medicine over at the Brigham and in the division of genetics there. And sorry about the miscommunication.